Welcome back. This is my video on runtime analysis, a topic that I think a lot of students struggle with at first, especially if you're not used to being able to take a piece of code and say things about it with regards to how fast it is or how slow it is. And something that's going to be relevant for, I think, most of the rest of this course. There will obviously be times where you don't need to know the runtime of things, but it is something that's not only going to be important here, but also going to be important later on when you're implementing different algorithms, different programs, and trying to see, what's faster than what. Before we can really dig into runtime, how quick is a program, we need to review a little bit of math. Sorry, I do promise there won't be any calculus, but we do need to know summations, and series in particular are very important, mostly because when you think about it, what do a lot of programs have? They got loops in them. What is a loop? A loop is very often used for instance, if you're trying to sum a bunch of numbers, you use a loop to do it, right? You sum all the numbers in this list and add them up and do whatever. And usually when you're summing up things, you probably need to know summations. So just, starting from the very beginning, what does a summation look like? We got the big old sigma here. At the very bottom is the starting value of a variable. In this case, it's k. And at the top is how high we get up to. K basically goes from this number inclusive all the way up to this number also inclusive, and that's our summation. And inside is what we're actually adding up, so you can think of all these being added together. So some variable a with a subscript k, the sum of that, where k is 1 up to n, basically means the summation of a1 plus a2 plus a3 plus a4 all the way up until you hit an. So for example, if a sub k was just k squared, then what would you do? Well, you take the k, you substitute in the value 1, and you keep doing that and increasing by 1 every time until k is equal to n, which means you'd have 1 squared plus 2 squared plus 3 squared all the way up to n squared. So this slide has a bunch of identities. These are things that you're expected to be able to just pull out of your hat at any given moment. The reason is I'm going to show you them right now so that you can always remember them, since they are things that will become very useful to you anytime that you see one of these messy sigma characters and want to break it down into a simple formula. The first of these is something that hopefully you've seen before, which is basically the sum of k equals 1 of k up to n. Basically what this is saying is, what's the sum of 1 plus 2 plus 3 plus 4, so on, up to n? And the answer is n times n plus 1 over 2. This may seem like it comes out of kind of magic, but there is, an argument, a very simple one, that can be used to come up with where this shows out of. Imagine that someone just asked you, okay, give me the sum of numbers from 1 to 100. You could use the sort of naive approach of, okay, what's 1 plus 2? That's 3. What's that plus 3 is 6. That plus 4 is 10. And just keep adding. This is going to take you forever. Alternatively, you can be a little bit faster and think about it this way. Well, the first number we're adding is 1. The last number we're adding is 100. So we have 101 there. The second number is 2. The second last is 99. So that's also 101. Then we got 3 and 98, also 101. So really we're just adding a bunch of 101s over and over and over. How many are we adding? Well, basically we keep going all the way up until we hit 50 and 51. That's our last 101. So there's 50 of those, which is n over 2, where n is 100. So we have n plus 1s are 101s, and we got 50 of them, so we multiply, and boom, we have our answer of 5,050. If you want, you can always write a program to manually sum up the 1 to 100 if you want to see why I'm right. Now, that's our really basic arithmetic summation. What about the geometric series? So this is the sum where k equals 0 up to n of q to the power of k, where q is some number. We'll denote this by s. Now, this is something that's kind of messy to work with, and immediately is something you're probably going to want to try to get rid of if you're doing any math. How can we do so? There's a few little tricky things we can do to break this down into a much simpler form. First, let's consider what happens if you multiply by q. Well, if you multiply s by q, we get q times s. If you multiply everything in the series by q, well, what happens? The first term here we have is a 1, right? It's q to the 0, which is 1. Then we have q by itself, q squared, q cubed, and so on, all added together. Well, if we multiply each of those by q, well, our 1 is going to become q, our q is going to become q squared, our q squared is going to become q cubed, and so on up to the last, which is q to the n is going to become q to the n plus 1. So we can rewrite this sum by changing it so it starts from 1 and ends at n plus 1 of the exact same series. Okay, that's all well and good, but what can we do from here? Well, consider if we took the things that we started with, our original series, and we subtract this new value from that. So if we take what we had originally and subtract q times s, and so we have on the left here, what do we get? Well, in our original series, the only value that appears there that doesn't appear in the second one is q to the 0, in other words, 1. Now, what shows up in the second summation that doesn't show up in the first one? It's that last value, q to the n plus 1, that isn't in the other term. So we have positive 1, negative q to the n plus 1. Over here, you can see, s is a common factor, so if we factor out s, we have 1 minus q, move that underneath to the other side, and boom, we have a much simpler formula that you can directly compute without having to worry about k's or summations or anything like that. All right, some more properties of sums that you might need if you want to manipulate your information a little bit, and that can make this math a little bit simpler. First off, we know how to do the sum of k, where k is 1 up to n. But what happens if you have a multiplier in here? Well, it turns out if you have 1 plus 2 plus 3 up to n, and that's all multiplied by 5, so you actually have 5 plus 10 plus 15 plus so on, you can actually just factor out the 5, divide it out of all the terms, and leave it on the outside. So the sum of all the terms you have in there, multiplied by your alpha, your coefficient, is the same as if you had just added together the coefficient times each term. So that can make things a little bit easier to calculate since we know the value of this sum. What happens if you have the sum of terms that are added together? We have a subscript k and b subscript k. Well, it turns out since neither of these really depends on the other, you can rewrite this summation as two different summations where you have this sum here and this sum here. And you might be able to convert each of these into something using one of our identities. Now, for shorthand, let's suppose for a moment we let j just be k minus 1, right? And we have this summation here, which looks a little bit messy. We have the sum of k equals 2 up to m plus 1 of k minus 1. So if you substitute in here, what does this mean? Well, basically it means we have 2 minus 1 is 1, right? 3 minus 1 is 2, all the way up to m plus 1. Well, m plus 1 minus 1 is just m. So this probably sounds somewhat familiar to you, right? Turns out you can actually just rewrite this as the sum of j equals 1 of j all the way up to m. We've replaced this annoying k minus 1 term, which we're not really a big fan of. And by substituting in our j, which is k minus 1, we can actually just directly translate this into the identity that we saw from the last slide. Notably, you also could take this summation here and apply this to it as well, just directly ripping out the 1 and taking its sum from here to here. But because these indices are kind of annoying, we don't have k starting at 1, we have it starting from 2, and we have m plus 1 instead of what we want. You could manually manipulate the indices in a different way, or you can do what I proposed here, which is just a direct substitution that makes things a little bit more direct. All right, now, talking about runtime. Generally, when people, programmers, computer scientists specifically, talk about runtime, they almost never talk about it in terms of actual time, seconds. So you're not going to hear anybody say, oh, my code runs in 1 millisecond. No one ever says that, right? Instead, what you hear is something like, oh, my code runs in big O of n time, or big O of log n time. And that's what you're going to learn in this course, is how we can talk about things in a different way than just referring to time, mostly because technology changes. Way back, long before I was born, 55 years ago, if you took an old IBM mainframe, one of those gigantic computers, and tried to do a single Bitcoin hash, it takes you 80 seconds. And now today, you can grab a modern Antminer S9, and it can do 14,000 of those hashes in a single second. So talking about how quick your code goes in terms of time, kind of meaningless when a lot of it is really dependent on something like hardware. So the idea talking about running time is that it is proportional to a function of the number of steps carried out by the computer running code. Generally, we assume simple things like arithmetic or a variable assignment take 1 step. And very often what we're concerned with was, okay, how many steps are we going to end up with in total, given that very often our code has things like loops, which might mean that this operation here, j equals 0, might run a whole bunch of times because this loop might run a whole bunch of times. And so being able to count this out is, a summation problem most of the time, and is why we need to be able to figure that sort of thing out when we're talking about how slow or how fast this is going to be. So, a practice problem for you to try out before class, and we'll talk about it in the class, is these two quick true or false questions. Is the t of n, which is the running time in terms of the number of steps taken for this code, equal to n squared over 2 plus 2n plus 2 when n is an even number? And then true or false is t of n squared over 2 plus n plus 1/2 for odd n. One of these true, one of these false. Well, something to think about before class. Now, I want to cheat a little bit and help you out by giving you the answer to one of these. And so we're going to look at specifically what happens when n is an odd number. So let me pull myself out of the way a little bit here so you can see up here is the code that we're working with, and over here is my work. And so I'll go through it line by line so you can see where all this came from. Okay, so starting off, because we know that n is an odd number, now we want to deal with fractions. Anytime you have summations, fractions really should not be in there, so we're going to eliminate them completely by only talking about m instead of n. M here we're going to say is n minus 1 over 2, and since n is an odd number, this means that m is a whole number. Okay, so if we keep that in mind, what can we say about the running time of this code? Well, to start off, the first line of code is always just going to be one step. Anytime we call this function, I equals 1 is just going to take one step, okay? Similarly, comparing I less than n is going to happen no matter what n is, even if n is 0, and is another step that we're going to take. So the total number of constant steps, independent of all this loop stuff we're going to see later, is going to be 2. One for the check, one for the assignment. Okay, now inside here we have a summation. So there's a loop here. So the number of steps that go on inside this loop is a summation of how much happens in a single loop, and then that's incremented as we go through each loop, right? Every time that we go through a loop, we have to add up extra work that's done in there. So how many times does this loop go through? Well, assuming that that m is greater than 1, then the summation starts from one iteration, k equals 1, all the way up to m. M is the number of times this is going to run because we can see that, well, I is going to go up by 2. This is something we'll need to, keep track of since that's the variable that determines how often our loop goes, which means that I is going to be 1, then 3, then 5, then 7, and so on, up to n minus 1 inclusive. We know we're going to be able to get to n minus 1. But now how many times is this, right? Well, the number of times is, it's not n minus 1 times, it's n minus 1 over 2 times, because we're skipping up by 2 every step. So that's how many iterations we have of this loop. It's m, n minus 1 over 2. Now in here, how many steps are there? Well, j equals 0, that's a step. Comparing j to I, that's another step. Ignoring for the moment that this loop might run and have a bunch, we're just looking at the constant steps right now. I equals I plus 2, that's another step. And then finally, we have to check again to see if we can leave the loop now. I less than n, true or false. So we got 4 steps that happen regardless of the loop inside of here. So this is where this 4 comes from. And then we have another loop. How many times does this loop run? Well, this loop has j less than I. So we want to look at how do these two compare, and also what is the rate at which j goes up? Well, it turns out j goes up by 1 every time. So we start j at 1. And how many times do we get to? Well, over here I've written 2k minus 1. Where the heck does that come from? Well, think about it. I at the very beginning starts out as 1, right? So that means that the very first time that we run this loop, how many times is this loop going to go through? Well, 2 times 1 minus 1 is 1. So we get it once, right? Okay, cool. How about the next time? K, in our second iteration of this loop with the I less than n, is now at 2. Sorry, not at 2. On the second iteration, it's at 3, right? Because we've added I equals I plus 2. So now we're at I is 3. How many times is this loop going to go? Well, j starts at 0, and if I is 3, then we got 0, 1, and 2. That's 3 iterations. So k times 2 times k is 2 times 2, that's 4, minus 1 is 3. So this sum is going to go 3 times. So hopefully you can kind of see from here the argument for where this upper limit comes from, which is basically the value of I. Now, in this loop, how many steps do we have? We have j is j plus 1, that's a step, and then we also see if we leave the loop, j is j less than I. So 2 steps total inside this loop, which is where this 2 comes from. So that is this entire formula above my little red dot, showing you what is the runtime, including the summations of this function. Now, okay, great. We've got the runtime with summations, but that's pretty messy, right? We want to break this down into just something I can punch in a calculator. So, okay, first off, important thing to remember is this can be calculated very, very easily by just straight up multiplying inside. We know that j doesn't affect the number 2, so literally all we're doing here is we're just taking 2k minus 1 2's, which means we're multiplying, so 2 times 2k minus 1, okay? Now, that being said, we can simplify this a little bit because we see we have plus 2 here, minus 1 here, we can multiply inside. There's a positive 4, so 4 minus 2 gives us plus 2, and 2 times 2k gives us 4k. So simplify it down a little bit into here. Okay, and now how about this one? Well, we can once again see that k doesn't affect the 2. So how many 2's are we going to end up with? M of them. So you got 2m. And then what do we have left? We can take the 4 out of here because 4 doesn't really have any impact on the sum. This is again from I think the second or third, I think it's the second, third slide of this presentation. Removing the 4 out gives us the sum of k equals 1 of k up to m. And we know that's our m plus 1 over 2 formula that we got from before. Now, doing a little bit of simplification here, 2 cuts this in half, so we're left with 2 instead of 4. We can multiply this inside, so we have 2m squared. We have 2m times 1, so that's 2m, plus this 2m gives us 4m. So, okay, we got 2 plus 4m plus 2m squared. Now at this point we want to turn this back into n, right? Because we originally were asking, okay, what's the t of n? What is the time in terms of n that it takes to get this to go? So taking m and replacing it with our original formula for it, n minus 1 over 2, what do we get? Well, we'll put all the terms in here. Okay, now this divides by 2, can divide out that 4, so and then we're left with 2 times n times 1, so we got 2 plus 2n minus 2, because that's 2 times minus 1. And then what do we have over here? We have 2 divided by 4. We can cut this in half, so this is just 1 over 2. And then n minus 1 squared is equal to n squared minus 2n plus 1. Okay, let's try to take stuff out of the brackets. So n squared, this is the only n squared we have, so that's just going to be divided by 2. We can't do much with it. Minus 2n divided by 2 gives us a single n. Remove that from our 2n, we're left with 1n. And then how many positives? We got plus 2, minus 2, plus 1 half. So this and this cancel out. So we are left with a positive n squared over 2 and a half, which is n squared over 2 plus n plus a half. And if we go back over here, look at that, n squared over 2 plus n plus a half for our odd n. Is the top one correct for even n? I'll leave that for you to try out, and we'll talk about it in the class. So counting steps is a big part of what we were just doing, right? And so when it comes to figuring out the complexity of a whole piece of code, very often what we find is convenient for us to do is to actually look at the line of code that gets run the most, right? Now, if we look at this program here, okay, ignoring the whole process we just went through and just looking at which line of code here probably gets executed more than any other line of code. Well, it's got to be the one in the inside, right? No matter how many, like assuming that these loops run more than 0 times, which I hope we can assume. If it's less than that, it's so trivial that we don't care. Assuming these loops are running a bunch, the line of code inside those loops gets run the most times. We're going to hit this line of code a lot if n happens to be a big number. So since this line of code occurs at least as often as every other line of code, really what we want to do is just figure out how many times does this line of code run, and we just use that as our determiner, right? When we were looking at the last exercise that we did where we had n squared over 2 plus n plus 1/2, in the end we actually really only care about that first term, that n squared, because that, once n gets to a really big number, is the one that's going to make the biggest impact on how quick this code goes. So let's consider the following. Here's a function. Total is 0. I goes up to n. J goes from I to n. And we add to our total and return a value. Okay. Here is a practice problem for you to think about, and we'll talk about in class. Looking at this line of code here, total equals total plus 1. That's the one that's marked with asterisk. What is a tight bound on this code based on the count of that line? In other words, when you do like the steps that I showed you earlier, what do you end up getting for how many times this line of code runs? Is it n squared, n minus I, n squared over 2? Think about it, and again, we'll talk about it in class. Okay, more summations, sorry. Turns out when you have a loop inside a loop, we very often are going to see things that look like this, these kinds of summations, right? The last piece of code that I just showed you is one in particular where we have a loop that runs from I to n, and then another loop that runs from j or k up to I. And what do you do with this, right? Well, turns out that you can actually simplify this a fair bit by considering that we know what this first identity is, right? We know what the sum of for k, where k is 1 up to I is, and it's this summation, right? The I times I plus 1 over 2. So if we replace this whole thing with I times I plus 1 over 2, we're left with this little formula, which is at least a little bit easier to work with. So let's put some of this into practice. Taking a look at a couple of code examples that I have here. We'll start with the first one, then go over the second one, but you can hop back if you need to see the code again. In our first example here, which is this code, we have s1 equals 0. I is going to go from 1 to n plus 1. In other words, it's going to go n times, right? S2 starts at 0. K is going to go up from 1 to I plus 1. And inside that, we have S2 is S2 plus K. S1 is the sum of S1 and S2. We return S1 at the end. Okay. Something important to remember when we're talking about runtime is we actually don't really care too much right away about what is actually happening here. You could probably go through and figure out, okay, what are these numbers? What's this 0? What's this K? What's this S2? But when we're discussing runtime, only really care about how fast is this actually going, right? Which means that the only thing you should really take away from lines like this one, where S1 is S1 plus S2, is that this takes a constant amount of time to run. Another thing that we should consider is that when we're discussing big O, runtime, where we care mostly about that very first largest term in terms of n, so like n squared, n, and so on. When you have n equal to something like a billion, and you have some constant number, like in here, how many constant time operations do we have? We have S1 is 0, that's 1, and for I, is I less than n plus 1, that's 2. At some point, it's just not worth anybody's time to do that kind of like itty-bitty calculations. So what we end up mostly doing in computer science is when we look at functions like these, we just say, okay, there's some amount of constant work that's done that doesn't depend on n. We don't care about how big n is when we assign 0 to this variable. We don't care about how big n is when we have to compare to the value of n. So we just say, you know what? The constant time outside of these loops that this program takes is 1. So we write a 1 here. Okay, now how about inside the loops? Well, fortunately we're using range in here, so we know that this is actually just going to run n times. So we're going to have a loop that goes from I equals 1 up to n of some term a sub I, which is however much it takes to go inside this loop. Well, how much is inside this loop? There's some constant stuff. We're just going to call it a 1. Who wants to sit here counting exactly how many operations? It's not worth anybody's time. There's 1, and now inside is another loop, right? Okay, well, how many times does this loop run? This loop runs I times, right? We can, from 1 to I plus 1 is I. So that actually just means that a sub I, the amount of work that gets done in this outer loop here, is just 1 plus what gets done in here. Well, I. There's a constant amount of work that happens inside of it, but who cares? And 1 times I is I. So what we end up with is 1 plus our summation, and our summation is of constant 1 plus I. And this is really simple to work out, actually, right? Because we know, well, the summation of these two terms is equal to the two summations of both. So we have 1 plus the sum of 1 and the sum of I. The sum of 1 n times is just n. The sum of this is our little formula, n times n plus 1 over 2. So add all this together, what do we get? 1 plus 3n over 2 plus n squared over 2. And at the end of the day, really we just care about this n squared over 2. Sometimes you don't even care about the over 2. Again, when n is a billion, and let's suppose we're talking about our bank accounts, right? If n squared was a billion, would you really be super upset if you suddenly had only 500 million and not a billion? Considering how much you currently may have, that's probably the metric that you should use for determining, do you really care that much about some of these little itty bitty values on the side? Okay, how about the runtime of this one? This one looks like it could be really messy, right? We have this like little wild line of code in here, and what happens in this code? We got constant time operations, so that's 1. What happens in here, we have this loop runs n times, and constant amount of work, so pretty simple. It's 1 plus n. That's all pretty quick and easy, right? Well, now that we've done that, let's actually go back and do the kind of the opposite of what I said before, which is let's look at what were these functions actually doing. Well, if we back up a little bit, okay, what's happening in here? We got I is going up from 1 to n plus 1, so this loop's going to go n times. We got S1 and S2. K is going to go up to I. S2 is going to be S2 plus K. Okay, let's think of some numbers that are actually going in here, right? So at the very beginning here, we start out with S2 is 0. And then we're going to start to, well, what are we doing here? We're actually summing, right? This code here is actually doing the summation of the numbers from 1 up to I plus 1, right? So, 1 plus 2 plus 3 plus 4 up to I plus 1, and we add that to our summation. And so something you might realize actually as well, if you compare this code and this code, this is actually doing the same thing, right? It's taking our summation that starts at 0, and every time we're iterating through our loop, we're adding the sum of numbers up to I. And well, we know what the sum of numbers up to I is, right? It's I times I plus 1 over 2. So if we actually just put that formula in here, turns out these two pieces of code do the same thing, but do it in very different speeds, because n squared over 2, when n is a billion, that's pretty huge, considering this is just 1 plus n. Now, this sort of leads into why we mostly care about functions based on their growth, especially at very large values. So when you think of, if someone were to ask you, how big is a turkey versus a chicken? Most of the time you're not really thinking about a baby turkey or a baby chicken, because it might be the case that a baby chicken could be bigger than a baby turkey. I don't know, I'm not a biologist. But we only really care beyond a certain threshold. At some point you reach this moment where the turkey's just always going to be bigger than the chicken. And similarly for our code, there kind of ends up reaching a specific point where all those constants don't make any difference, and you really just care about what happens for really, really big, and generally input size is the thing that we're graphing for these functions. So first, let's talk about what's a positive function. So a positive function, and let's read this through mathematically the way that we learned There is a number in the naturals called n naught, such that for all natural numbers, if that natural number is bigger than n naught, then our function is positive. So if you think about it, think of something like, maybe like you have a sine wave, but once you hit n is 10, suddenly it just skyrockets off of the, like above the x-axis and is never, ever, ever, ever negative. This is a positive function. And turns out, pretty much all code that you'll ever see, if we're calculating how much time it takes to run, well, since we have not yet discovered code that allows us to go back in time, means that the time it takes to run code based on its input size is pretty much always going to be positive, which means we need this to represent our runtime. Where f of n is a function, so this is, it's positive. Okay, something that you should have seen, I believe in CSC236, because I remember showing this to people in CSC236, is, and probably in math as well, is the relationship between function growth of different functions. So these are functions you probably should be somewhat familiar with in terms of what they look like. Now, when we're talking about which of these, grows faster than others, 1 is pretty much the slowest growth rate because it doesn't grow. It's just always 1. Log n doesn't grow too fast. Root n grows faster than log n, but is still obviously not too fast. N is linear. And log n is a little faster than linear. N squared is clearly faster. Now we're curving. N cubed is faster than n squared. 2 to the n is faster than all the stuff below. This is where it starts to really skyrocket. And n to the n, of course, goes kind of off the charts really quickly. Now, importantly, this is obviously we know this is not true for low values of n, right? When we look at something like n is 0.1, we might see some of this doesn't actually hold true. 1 is definitely greater than 0.1, but we don't care about that level of little numbers. Mostly this is when we're talking about n is something really, really, really big, in which case if n is 1,000,000, when you compare all of these formulas and plug in n equals 1,000,000, you literally can order these exactly as they are. Okay, this brings us to big O, and we're going to talk about it very formally in this course and have a specific definition for it. So big O looks something like this. A function g that maps from naturals to real numbers is big O of f of n for some function that also maps naturals to real numbers if and only if there's some constant in the rationals, positive rationals, and there exists an n naught in the naturals, such that for all natural numbers, if n is bigger than n naught, basically once you're past that threshold I've been talking about, g of n is less than c times f of n. Now we can pick c to be whatever we want, and that's sort of the beauty of doing some of these big O proofs, is we can usually pick a c that happens to suit our interests, but it turns out that the importance of this is that, let's suppose that, g of n was a linear function, and f of n was quadratic, right? Can you pick a multiplier, some positive real number, where you can multiply the quadratic and it'll ever be less than linear? Nah. Eventually, n will get so big that no matter what real number you've picked, that curve is going to go over. It's going to go above the line, no matter what. And so, when we're talking about big O, really what we mean is the rate of growth of f of n bigger than g of n? Now, again, we're leaving calculus out of this, so we're not touching derivatives, we're not touching integrals, any of that stuff. Usually we can actually just figure this out simply by, first off, knowing the differences between some of those functions as I mentioned before, knowing that n squared is always going to end up being bigger than n, no matter what constant you have multiplying it, and that's really the argument that is the crux of doing some of these big O proofs. Okay, so let's look at a really simple big O proof. Let me move myself out of the way. Okay, here we go. So here's definition of big O at the top. And let's suppose we want to do two little simple examples. Okay, we want to show that 1 plus n is in big O of n. What does that mean? What that means is that if I were to graph 1 plus n, and I were to graph n, can I think of a multiplier where if I multiplied n by that, it would always be above n plus 1? Well, that's actually pretty simple. And also, what is, sorry, second part of the big O proof is what is the threshold for which that actually holds true? Well, it turns out I can keep this really simple. Suppose I start at x is 1, then what do I have? I have 1 over here and 2 over here, right? So, okay, well, what if I make my multiplier for n equal to 2? Well, in that case, as soon as we hit n equals 1, they're going to be the same. And everything beyond that, 2n is going to be bigger than 1 plus n. So I've chosen c is 2, n naught is 1, and this now means that n is an upper bound, which is what big O is, of n plus 1. Or specifically cn is an upper bound of n plus 1, which is our big O proof. All right, how about this one? This was the time complexity of the sloppier calculation for a summation that we saw a couple slides ago. And I mentioned before that the term we care about mostly is the biggest one. So in this case, the n squared. We want to show that that is big O of n squared. In other words, we can come up with some multiplier and a threshold after which big c times n squared is always going to be bigger than what's on the left. Okay, well, let's start off by picking 2 for fun. Also because it makes dealing with the fractions less annoying. Something that's convenient again for these big O proofs is you can always pick an like somewhat larger values of n if it does help you do some of your math a little bit easier. In this case, I'm just going to keep it simple. N is 2. Okay, what do we have then? Well, if n is 2, if n is at least 2, then what happens if I do the following, right? I can take what we originally have here, and I can say, well, as long as n is bigger than 2, then clearly 1 is less than n. 3 over 2n is less than 2n, and we'll just leave this here. Okay, so I have this clear inequality, right? And I think it's pretty straightforward to see why this is true. Okay, now that I know that that's true, well, n is less than n squared. I think we can see that for sure. 2n is equal to n squared when n is exactly 2, and as long as n is bigger, then n squared is strictly larger. And we can leave the n squared over 2 here. Now we can actually add these all together because they're all n squared, right? And so now we have 5n squared over 2. So, hey, look, 5 over 2 is it's a constant I can pick. All right, I choose c is 5 over 2, and my n naught is 2. And look at that. If I have 5n squared over 2, beyond the threshold of n equals 2, that's always going to be bigger than 1 plus 3n over 2 plus n squared over 2, which completes the big O proof. Okay, now, so far these big O proofs seem like it's just always going to work if you do the math correctly, right? Well, it turns out that we can find situations where it's not always the case. So here, let's suppose that we were being foolish and we decided to say, you know what, we think that n squared is in big O of n, or suppose we formally want to say that this is not in big O of n. Well, if you want to show that something is not in this set, well, what did we learn at the very beginning of the course? With a proof by contradiction, we negate everything. In other words, let's suppose that this is in big O of n, and we'll show that that leads to a contradiction. All right, well, if this is the case, then that means that this formula is less than c of n for some n, right? And so if that's true, then we also consider that this is greater than or equal to n squared over 2, then we can, ignore the formula completely and just look at these comparisons. Well, we know that c of n must be bigger and n squared must be smaller. So we suddenly have n squared is less than or equal to 2 times cn. In other words, meaning that we need to choose a c such that n is less than or equal to 2c for all natural numbers. Well, you can't, right? Whatever constant you tell me, n is going to eventually be bigger than that. So this is impossible. And since this is impossible, our original assumption that this is in big O of n must be false. All right, so let me move myself again. And we will discuss big omega and big theta. So far what we've talked about is big O, that is upper bounds, sort of the maximum runtime that our code can take. However, we also care about the lower bounds of how much our code can take in terms of runtime, and specifically tighter bounds if we know exactly how much it's going to be in terms of steps. So a function is in big omega of another function. If this is sort of the same formula you saw with big O, except instead we have our g of n is bigger than c times the function. And so importantly, because c, that constant we were talking about, can be any real positive number, very often the c that we're going to pick is going to be a fraction. Could be a half or something like that. To show something is in big theta, a function g being in big theta of f of n basically means that g needs to be big O of f and big omega of f. In other words, we can say that the function n plus 1 is in big theta of n because we can pick a constant that's going to lead us to a bigger bound, and I'll pick the constant 2. 2 of n is going to be bigger than n plus 1 pretty much all the time past the number 2. And we can pick a lower bound as well by, say, choosing a half. 1/2 n is going to be less than n plus 1 pretty much the whole way through. So by finding a constant multiplier that I can apply to my function, that makes it so it's an upper bound and a lower bound, means I have what's called a big theta bound. It is a tight bound on the complexity or runtime of a piece of code. So here's sort of like the formal way that you do it. To say that m plus 1 is in big theta or big omega of n, we need to pick a c such that 1 plus n is bigger or equal to that. I can actually do it better than picking a half. I can just pick 1. It turns out if I pick my constant to be 1 and n naught is literally anything, 0, 1 plus n is going to be bigger than n the whole way through. That's, I think, something that's not too hard to see. Now, this brings us to the question of, okay, why do we care about any of this, right? Why are we learning big omega, big O? These notations can be used to determine asymptotic runtime of an algorithm. In other words, what happens while the value of n starts to become very, very, very big. For iterative algorithms where we have loops, the strategy is usually to sum the total amount of work done by the algorithm and then determine a theta bound from that sum. In this course, we're going to focus specifically on worst case analysis. That is, what is the runtime of the code, assuming we get like the worst possible scenario. For instance, if we have some code where we're searching for something, suppose what we're searching for isn't there, then we usually have to look through the maximum number of stuff, depending on our algorithm, of course. So when we ask the question, what is the worst case, we're saying is, what is the maximum number of operations used by the algorithm for an input of size n? Importantly, what we're saying here is nothing about the format of our input. For instance, we're not really saying anything about, is our input an even list? Maybe we have a function where if it's an even list, the runtime is 0 because we ignore all even lists, something like that. Those are not the kinds of cases that we care about because that's not the worst case. The worst case is when our input is a very large arbitrary size, and we want to see in the absolute terrible scenario where we have to run as much code as we can, what is the number of operations that happens. Let's look at a really simple piece of code and argue about its theta bound. So here's our code over here. It is we are checking a list to see if it has an odd number. And so the way we do it is we look through everything in the list. If it's odd, we return true, and if it's not, we return false. Kind of a simple piece of code, right? When we talk about worst case, what we're saying is, in the worst case, we don't find an odd number because that means we have to do the most work possible. You surely could come up with a very, very large input where the odd number is the first one, in which case the runtime is really fast. But we don't care about that for this course. We're just going to focus specifically on worst case. So what can we say about the runtime here? Well, in terms of big O, we can look at it and say, okay, what's how much time is this going to take to go through? Well, this loop goes through n times because there's n elements in our list, plus a constant amount of work, some amount. And so we can definitely say that our function is in big O of n. It seems kind of easy. We pick c is 2, n naught is 1, and hey, look at that, we got what we wanted. Now, let's suppose that we want to look at the big omega, right? We want to look at what actually happens for our worst case scenario. What is the list going to look like? Well, the worst case list I can think of for size n is this list. It's 0, 0, 0. It's just all zeros. There are no odd numbers in there, right? So what's the least number of lines of code I can get to run on that? Well, it turns out you're kind of screwed either way. No matter what, you're just going to have to run through and it's going to have to take at least n steps to go through, because there's no way you can figure out if there's an odd number without having to look through each of the n values. Because of that, we know that the time that it takes is at least n, so our code is big omega of n. It's going to take n lines of code or more no matter what, assuming we're looking at the worst case. If it's big O of n and it's big omega of n, it therefore must be big theta of n. Now, at this point, you're probably wondering, okay, is it possible, like it seems like almost every scenario we're looking at, our code has big O and big omega of the same thing, right? So is it really even possible for a program not to have a tight theta bound on its runtime? And, there is an example of that. Here's our code, and what this code is going to do is generate a list of primes for us up to n. And so the way we do it is we start with our list that doesn't have any primes in it right away. We start from 2 and we're going up to n inclusive. If k is a prime, then we add it to our list. Then we return list at the end. So we're adding all of the first primes that are equal or less than n. And how do we know if something is a prime? Well, we look through all the numbers that are less than that. Is it evenly divisible by that number? If so, it's not a prime. Otherwise, it is a prime. Does this have a tight theta bound? Well, let's take a look. So let's start by looking at the simplest runtime to go through, which is what's the runtime of this code here? Is prime, determining if something is a prime number or not. Well, this loop runs k minus 2 times, goes from 0 to k minus the first 2, in the worst case, assuming that the number is prime. So the worst case runtime of this is k minus 2. T1 of k is is going to be no greater than k minus 2. Now, how about the runtime of this code? Well, assuming that, in some weird scenario, we were able to run, every time we run is prime, it never ever actually returns false. It always forces to return true. That means in those scenarios, we have the summation of how many times does this loop run. K starts at 2 and goes up to n inclusive. So we have our sum here of k minus 2, which is in O of n squared. If you're not sure why, remember our summation from before, and you can maybe do the math yourself in case you forgot. Now, how about the lower bound in terms of, considering the fact that sometimes this actually will return prematurely and save us a little bit of effort? Well, that means we just really need to care mostly about the cases where the numbers are prime. So the runtime of our code is, and you can say this in your head to convince yourself it's true, is greater than or equal to the runtime, the summation of steps that it takes for all the primes that are k between 2 and n, running our is prime function, which takes k minus 2 steps. Now, splitting up the sum, we can separate the k and the minus 2 and factor out minus 2, leaving us with just 1. This leads to the question, how many primes are there between 2 and n? And the answer is about n over log n. And so that's how many times that our loop goes through. We're summing k, so that's how many times you have to add the k's together. You basically end up with this little formula, sum constant, we don't care too much about the constants, times n squared over log n minus, over here, we have n log n times, some constant. Putting constants aside for a moment, we can pretty quickly see if we just pick a big enough or a small enough constant, this is larger than c times n squared over log n. In fact, you can just pick this c to be, if you pick the c to be big enough, you can have that inequality hold. So what we've shown here is that the runtime of this is greater or equal to c times n squared over log n, which means that it's in big omega of n squared over log n, which is a different bound from our big O of n squared, meaning that there is no tight theta bound for this code. So now that we've seen, definitions of big O, big omega, big theta, Let's consider the following. Which of the following things here implies that f of n grows faster than g of n? Is it that f of n is in big O of g, f of n is in big theta of g, f of n is in big omega of g, or none of these? Think about it and we'll talk about it in class. Another question, which of the following is true? F of n is in big O of g implies f of n is in big omega of g. F is in big omega of g implies f is in big O of g. F is in big omega of g implies f is in big theta of g. F is in big theta of g implies f is in big omega of g. Now, more practice questions. Suppose f1 is in big O of g of 1, f2 is in big O of g of 2. What can we say about f1 times f2? Is it in big O of g1 plus g2, big O of g1 times g2, big O of the maximum of g1 or g2, or big theta of g1 plus g2? Keeping on with the practice questions, suppose f is our set of positive functions, as I defined before. Is the following statement true or false? There is an f in the set of positive functions and a g in the set of positive functions where f is not in big O of g and g is not in big O of f. True or false? More practice. Consider the following Python code. Here's the code here. You can look at it. From the following, what are all the correct type bounds for the time complexity of this code? Big theta of n squared, big theta of n, big theta of n log n, or big theta of log n. Keeping on. Suppose that we have f is in big omega of g, g is in big omega of h, and we want to prove that f is in big omega of h. From the first point, we know that there exist positive constants n1 and c1, or n0 if you prefer, such that f is greater than c1 times g for all n greater than n1. From the second one, we know that there are positive constants n2 and c2, such that g is greater than or equal to c2 times h for all n greater than n2. Now, f is greater than or equal to c1 times g, which itself is greater than c1 times c2 times h. Suppose that we have all that. Which of the following completes the proof? We choose our n0 to be n1 plus n2 and our c to be c1 plus c2, our n0 to be n1 plus n2, our c to be c1 times c2, n0 to be the minimum of n1 or n2, and c to be the summation, or n0 to be the minimum of n1, n2, and c to be the multiplication, c1 times c2. Just as some more practice, let's find and prove a theta bound. And for this, we're looking at the function 2n log n minus 2n plus 2. And we want to show that this is in a tight theta bound. Let's go through the proof. If we want to prove something is in big theta, we need to show it's big O and big omega. So first off, we probably want to figure out what is this going to be in big theta of. And just looking at the biggest terms here, we have 2n and log n. So probably we want to be looking at big theta of n log n, right? Ignoring the constants, just looking at the n's and the functions around them, that's what we care about. Okay, so to show that, well, we need to figure out what a value of c and a value of n0 so that we can always be bigger than that. Well, if we have 2n log n minus 2n plus 2, we know that that is lower than just if we ignored the negative term, right? We just have 2n log n plus 2. Okay, that in itself is smaller than 3n log n, assuming n is at least 2, right? If we have n to be at least 2, we can say that, 6 here is going to be bigger than, basically having the value here in these two values of n is going to help us overcome the fact that we're losing the plus 2 out of the side. So if we choose c to be 3 and n0 to be 2, we can show that f is in big O of n log n. That's half our proof done. Second half, we want to show that we can pick a c and an n0 that's smaller for n log n. So taking our original formula, 2n log n minus 2n plus 2, we know that's bigger than if we just cut out the plus 2 part, so we'll leave that aside. Okay, now let's let's solve a little bit, try to figure out when these are equal, right? If we want to try to figure out what happens when n log n is equal to 2n, just putting in the math here, n is equal to 4. And if you're not sure, remember that the logs that we're doing in this course are always base 2. So, log base 2 of 4 is, 2, and is 4. 4 times 2, 8. 4 times 2, 8. Okay, so that's where we know that these are equivalent, right? All right, well, 2n log n minus 2n is going to be bigger than just straight up n log n, assuming you've gotten to at least n to be 4. Once you've hit n is 4, then having an extra log n over here overcomes the fact that you have a negative 2n. So we just choose our constant to be 1, our n naught to be 4, and now we've shown that our function is in big omega of n log n. And since it is in big O of n log n and big omega of n log n, we can therefore argue it is in big theta of n log n.